Okay, let's move part 4, lecture 2. Lecture 2, definition of covariant metric. That's very, very important that will be used in many derivation ahead. Now, you see, from the previous video, see, this here, a tangent vector. So, this is 1, this is 2, this is A3. You see that they are covariant basis vectors, which is right over here, the definition. Now, what is important that these basis vectors, okay, let's put here. It's a very, very important point. They are not necessarily orthogonal. That is AI dot AJ, the dot product between AI and AJ, they, in general, they are different from 0. This is a scalar, okay? This, in general, they are different from 0. Could be 0, okay, in a special situations, and could be orthonormal, okay? Now, that's a point I'd like to make here. And also, I can write R is a function of x1, x2, x3. Do you remember? This is invariant. Likewise, from here, dr is equal, let's say this, EI dxi. You see, dr. If you expand this, this will be dx1 E1 plus dx2 E2 plus dx3 E3. You see, also, you can look at here, okay? This is also invariant. Okay? So, that's a point I'd like to, here, this is U1, E2, and E3. So, it's invariant. So, dr, the same dr, can be expressed, see, in rectangular coordinate. Cylindrical coordinate doesn't matter. See, that's very important. But again, I'll emphasize, these are no orthogonal base in general. Okay? Now, I erase here. Let's define the metric, okay? The covariant metric. Let's put here. The covariant metric Gij. It is defined as the dot product of AI dot AJ. You see? In R3, this is I can represent as a matrix, 3 by 3 matrix. Attention now, this is equal to AJ dot AI. So this is equal GJI. You see? Jij is equal GJI. Okay? That's what I say. This is symmetric. It is symmetric. So I could represent the metric as a matrix. Matrix like that. So Gij, I'll write here. Okay. So Gij is represented, Gij is represented as a matrix G11, G12, G13, G21, G22, and G23, and G31, G32, and G33. But, you see, since they are symmetric, they are equal, okay? This is equal to this, okay? And this is equal to this, okay? Because they are symmetric. That's a very, very important, okay? Then I will show you next time that actually Gij, in general, normally they call a tensor, second order tensor, because Ij are free indices. You see? Ij, I, comma, J are free indices. Okay? So, in general, as I was saying, that in the literature they call G's as a second order tensor. Second order tensor. Next video, I will talk about this. Okay? Actually, in my viewpoint, this is not a second order tensor. These are components of a second order tensor. Okay? I would like to emphasize this, but normally in the literature, when you see, oh, Gij is a second order tensor, okay, you accept. But rigorously, that's not true. Okay? I'll show you the lecture 3 about the tensor. This actually they call, I'll put this marker here. So what I'll show you that Gij are components of the second order tensor. Why? Because I'll show you this next time. Okay? I'll show. So you see, we are going step by step, okay? And also always review lecture 1, 2, and 3. Okay? Next will be lecture. It's a very, very important. Okay? The part 1, part 2, and part 3. okay? Just for us, for you, okay, to follow clearly, see? Just to understand this subject here, okay? Generalized coordinates.